Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, we'll get started. It's an honor today to have Ken Forbes with us. He's the Walter P. Murphy Professor of Computer Science and Professor of Education at Northwestern University. Ken received did his PhD work and his undergraduate work at MIT. He's been, in my mind, one of the core people over the decades working on challenges of representation and reasoning with qualitative knowledge, as well as doing analogical reasoning and learning, spatial reasoning. More recently, for my watching his work over the years, sketch understanding, natural language understanding. He's been a long-term advocate and leader in this realm of cognitive architectures. What's an architecture for reasoning about the world more generally? And he's been working in a number of areas, a number of application areas. He's a fellow of the AAAI, of the ACM, and of the Cognitive Science Society. He's received a number of awards for his work over the years, and it's always a pleasure to have him visit us. Ken.
Thank you, Eric, for that lovely introduction. So I'm going to talk to you today about some of the work we're doing involving learning from what we call bespoke data, custom data. And why bespoke data? Well, as y'all know, big data is a big thing these days. And my heavens, it's wonderful, right? Speech recognition is finally getting seriously good in many ways. Simultaneous translation in Skype, all sorts of great things it's capable of. But it's not what you want for everything. So for example, if you're teaching a child to understand stories and read, then you're actually interacting with that child. And if it takes that child 1 million times of being exposed to a word to learn it, you got a problem. There's evidence that actually human children can learn new nouns in a single exposure. So there's something we're doing that's very different than what today's machine learning systems can do. If you're teaching a child to do a jigsaw puzzle, or you're teaching an assistant a new task, you don't want to have to teach someone how to fill out a form 1 million times. You want to have data that's actually tuned towards your estimation of their capabilities and to be able to work with them effectively in the same kinds of range of examples that human collaborators take. Now, why do I care? Well, one of the things we're trying to do is actually achieve human-level AI. Now, if you think about today's AI systems, they're like drag racers. They're very efficient, they're very fast, okay? But like a drag racer, it does one thing. It's carefully crafted to do one thing. It has to be carefully maintained and babied and nursed back to health every time it falls down by carefully trained experts who know its internals in a way that we don't know each other's internals. If we did, cognitive science would be trivial, okay? So now think instead about dogs. You can task a dog to do all sorts of cool things, and they don't require a whole bunch of maintenance. You feed them, you give them some affection, they don't blue screen on you a lot, right? There's all sorts of great things. And what if our AI systems were as robust and trainable and taskable as mammals? One way I describe this sometimes is what we're trying to build is a 6th grade idiot savant from Mars. Okay, very smart, but clearly not from around here. Enough where we can communicate with it and work with it, but we're not trying to make something that passes for human. That's not the point. Now, the way we're doing this is a companion cognitive architecture. And what we've done is reformulate the goal in a way that I think is actually pretty productive. We're trying to build software social organisms, things that work with people using natural modalities. And for us, that means natural language and sketching. Those are sweet spots because natural language gives you expressive power, sketching gives you spatial aspects. Learn and adapt over extended periods of time. So things that can learn for weeks and months or years without having human beings maintaining them. And in fact, they should be maintaining themselves most of the time. We shouldn't have to know their internal representations, just as we don't know the internal representations of our assistants, our associates, or our children. Now, why social organisms? Well, first of all, it's going to make them very useful, but also I think that's actually essential to making things that are as smart as we are. Mike Tomasello has made this argument very plainly in several books now, and I think there's a lot of convincing evidence for it. Also, Vygotsky has argued that much of our knowledge is learned by interactions with people, and we actually call companions sometimes the first Vygotskian cognitive architecture. That's a goal, not an achievement. Okay, we're trying for that. And there's many things we understand that we've never directly experienced. So yes, you need to ground things in sensory information, but you know, none of us lived through the Revolutionary War. None of us have seen molecules directly, except with the aid of a whole bunch of very carefully crafted equipment. We see the results of plate tectonics, but that's inference as opposed to actually watching plate tectonics in action, given the time scale it happens. And same thing with most examples of evolution. So you have to have conceptual knowledge as well as physical knowledge. Now, if you think about cognitive architecture, there's been a lot of cognitive architectures, and some people, when they hear a new cognitive architecture, say, oh my lord, why one more? Well, if you think about it, Newell actually broke things down by time scale of tasks. So biological band with neural modeling, cognitive band thinking about skills, rational band more about problem solving and reasoning, social band, and in fact there's a developmental band above that. And if you look at most cognitive architectures, they focused here. So for instance, two of the leading architectures, ACT-R and SOAR, have as their signature phenomena skill learning. If you look at ACT-R, where they're going is down here. They've worked a lot to model fMRI data, for example. And where SOAR has been going is here. And so, for instance, they've had SOAR agents that run for many hours in training exercises, a real tour de force, and all sorts of stuff. And they're actually headed even further up. Companions, we care about these two bands. Just as when you're modeling a complex phenomena, you model it at multiple layers, and ultimately those models all have to talk together, you need to explore each layer. And you can't say, I'm going to solve this one before I solve that one, because we'd still be doing quantum mechanics. We wouldn't have chemistry and wouldn't have meteorology. Okay? And so you have to do things in parallel and talk to each other. So for us, we're starting here. We assume these folks are handling skill learning really well, and they are. But we're more interested in how you do reasoning and learning at these broader timescales. So that's the big idea of companions. And now I'm going to tell you about the hypotheses in a little bit more detail. I'm going to walk you through three kinds of examples. One is learning games, both strategy games and a very simple tic-tac-toe thing, and I'll show you a video of that. Learning spatial concepts and learning plausible reasoning. And one thing you'll see is that in all these cases, it doesn't take much data to actually learn these things. You can get a surprising amount if you know a lot and if you use analogical learning as your learning mechanism. So, by analogy, I mean Gettner's structure mapping theory. The idea is that analogy and similarity involve structured relational representations. So you have entities with relations connecting them up, and you're comparing one description, the base, against another description, the target. That gives rise to a bunch of correspondences saying what goes with what. And then if there's things in the base that don't have anything corresponding to the target, you can project those as candidate inferences to do a kind of pattern completion of these symbolic descriptions. Now, it turns out there's a substantial amount of psychological evidence supporting this model in phenomena ranging from high-level, medium-level vision, auditory learning, learning mental models, textbook problem solving, and conceptual change. And the evidence is both from purely psychological things with humans in laboratories like reaction time studies and protocol analyses, but then also computational modeling. So the story is actually pretty interesting. So we have these three hypotheses about human cognition, and we think that to build AIs, we need to actually take these seriously. The first is analogy as a central mechanism of reasoning and learning. A lot of things we think of as rule-based learning actually are probably applying something that's a high-level structure that still has some concrete stuff attached to it by analogy. Deidre Gittner's article, Why We're So Smart, is a very good introduction to this idea. The common sense is basically analogical and reasoning and learning from experience. So you start out by within-domain analogies, and they provide robustness and rapid predictions. When I go to start up a new car, and if it's the same kind of car I've had before, then I do the same thing, and that works. And I don't have to have a rule formalized saying, oh, it's a lock, I have to turn the key in the lock. Or it's one of those fancy fobs that I just keep in my pocket and I don't have to touch it. I just do it, okay? And now, so even one example, you can do an analogy to learn some other stuff, but we do generalize. And that generalization process gets us to first principles reasoning, but they emerge slowly as generalizations from examples. Now, by slowly, I don't mean millions. I mean dozens. Okay, so it's very different in terms of time scale. I think much more like what humans get. And qualitative representations are central to this. Qualitative representations provide a bridge between perception and cognition. They provide an appropriate level of understanding for communication and action and generalization. So those are like the three big hypotheses we're exploring. Now, there's these models we have of analogical processing. I'm not going to go into gory detail about each one of them because each one of them is an hour talk, but I'm going to give you a picture about how they all fit together, and that will show you how they get used in these subsequent things. So here, very roughly, is what we think happens. You have the structure mapping engine, which matches two descriptions, and these are either examples or generalizations, and the candidate inferences give you things like predictions or explanations or possible principles to apply in dealing with some new situation. Now, where do you get these things? You get them from your memory, of course, and we have a memory model called MacFac, many are called, few are chosen, that's designed to scale up to human-sized memories because the first stage is a cheap filter using flattened versions of the structured representations with a special kind of vector designed so that it predicts what SME will produce in terms of overall match quality. It's an inaccurate prediction, of course. That's why you have to do the second stage that actually uses SME over several examples in parallel. And that's where you get your stuff. And now the generalizations happen because you have basically another model which uses SME and MacFac to sit there and, given instances of a concept like models for a word, we've done this with spatial prepositions of contact, for example, in English and Dutch, you basically build up models analogically by combining these things using matching, keeping the stuff that's in common and deprecating the stuff that isn't in common by lowering its probability of being there. So with generalizations for us are probabilistic. We have a frequency information about every statement in them. They're partially abstracted. There can be very concrete things in them still. And they don't have logical variables. We don't need to go to variables because we can just use structure mapping to do the matching. Now, sometimes we do introduce variables. In fact, there's a couple of cases where we've gone through for various reasons and turned these things into hardcore, in real life logical rules or probabilistic rules. But that's not what we have to do by default to make knowledge useful. And that's the essence of how the companion architecture turns over, sort of high-level lessons. Yes?
Generalization, you said one of the things you do is you take a bunch of similar examples and abstract out the commonalities. How do you know what similar examples are similar?
So there's two answers to that question. First, we assume that there are generalization contexts that actually are sort of the analogical models you're building for a problem. Like, how do I interpret on? Or how do I interpret in? Another example, if I'm doing language processing and doing word sense disambiguation, for this word in this sense, what are the ways in which that's been used? Okay, so that's categorizing things in terms of relevance to a problem. Then to get the things that you compare against, you use the same retrieval model to retrieve from the pool of things you've been building up. So if two of them are sufficiently similar, you store the simulated version of those things back as a generalization, and the same retrieval model is used again. So you basically it's just, yeah.
I'm still not sure, like, so to Sue's question, like, so what is similarity? Like, is similarity like a general, like, what is the similarity metric?
Okay,
Does it have
similarity
is it
metric
different for different
is
structures?
computed, no, it's computed by SME. It's defined in advance, same similarity metric for word sense disambiguation, matching visual stimuli, story understanding, counterterrorism, moral reasoning, insanely robust. So it's the structural evaluation score that SME computes for two descriptions. So it really is that general. Okay, so here's some experiments that we've done early on. So learning physics from cross-domain analogies, you start with linear kinematics, a model of that, and a companion was able to learn rotational kinematics, electricity, and thermal problems. Now, MacFac retrieved the correct thing only 40% of the time. If you know the psychology of this, that's actually high. That's high because cross-domain analogies are relatively infrequent. Well, the beast didn't know much, so it's going to be able to find stuff more easily. And like humans, if you actually give it the precedent, it actually was able to transfer the information 87% of the time if it had that precedent. We've also done this for learning games. At 60 games, which were generated by an external contractor, experiment run by an external contractor, I think this is still the largest experiment in cross-domain analogies that anyone has ever done. So John Laird's group at Michigan developed a sort of basic game, which the contractor then went crazy over. You're trying to take this character and make it to the exit by building a bridge to escape. Tom Henrichs from our lab did a little version of Rogue, a mini version of Rogue. And there was a little version of Mummy Maze here, a variant of that. And what happened was you'd learn a game that you'd never seen before, and the companion would basically learn HTN strategies via experimentation. Now, it knew enough about games that if it couldn't master the game in 10 trials, it quit, because it never would. Okay. And these games are easily the complexity of the kind of Atari games that it takes the thing in nature 38 days to actually master. So I'm not so impressed by those results. Now, given one of those learn games as a base, you would then try to learn some new games, and you'd measure how much faster you learn. So positive regret is good. I would have learned 50% faster if I had the game almost 60% of the time. And there is some negative transfer. So 15% of the time, in fact, I'd learn 25% more slowly than if I didn't have the analogy. And so we're kind of excited about that. Now, modalities. We want natural interaction. That's still a really hard problem. That's still a very much an open research problem. And we made some progress, but, well, let me show you where we are. So our natural language approach is kind of different. We're focusing on deep understanding, all the way down to things you can do reasoning with, and we're willing to simplify syntax just like human cultures do with children. We're quite happy to simplify syntax because we want to go all the way to reasoning and decision making. We use James Allen's parser, research site knowledge-based contents. We've been building our own lexicon to replace Comlex. We use discourse representation theory for doing semantic interpretation as the representations for it. And we have a query-based abductive semantic interpreter. We use the idea of narrative function, trying to figure out what a statement's telling you in the context that you're working in. For example, in solving moral decision problems, the system is looking for a set of choices that it has to make and decide among. It's looking for the utilitarian cost of each decision, and it's also looking to see if any sacred values are involved. And it will basically decide in a human-like way what to do based on those factors. Interesting thing about that, those factors are the same for any moral decision problem. And normally abduction grows exponentially with the number of sentences. In this system, it actually grows with the number of questions you're asking, as opposed to the number of sentences. And so by basically formulating it as a top-down problem, you can do pretty well. So here's an example of some of the things you can express. Because of a dam on a river, 20 species of fish will be extinct. On the left is the predicate calculus with predicates drawn from the psych knowledge base. If you're going to implement DRT, the psych microtheory structure is your friend, okay? Because it's all about context. So these boxes, each of these boxes is a microtheory in psych with statements relating the microtheories to each other. So this is the DRT version of that same hunk of predicate calculus. Okay, so it takes some work, but it can be done. Now, what do you do with this? Well, one of the test beds we use is the strategy game FreeCiv. It's an open source version of Civilization 2. It's cool because it's got spatial concepts. You've got terrain of different types. You have to design transportation networks and figure out where to place your cities. You've got a complex economy. You can go bankrupt. You have guns and butter trade-off. You have investment versus immediate spending. There's all sorts of complex stuff in here. So it's a wonderful, rich domain. Now, one of the things you do when you think about this game, qualitative reasoning, a lot of it in dynamics grew up around engineering. When engineering, you have a blueprint, you know all the parts in advance, and that's a really simple world. In this world, it's not that way. In this world, you're reasoning about things that don't exist yet. You're reasoning things about reason about things that can get destroyed. So solely object-level representations are impractical when you've got limited attention and storage and processing time. If I have to build an explicit qualitative model for every tile in the game, I'm host, okay? That's not going to scale. And that you have to plan for things that don't exist yet. So you have to build models of the dynamics for things that don't exist. So we've introduced a kind of type-level qualitative model that uses predicates and collections as arguments. So for instance, QProp plus normally says the first quantity, shouldn't stand in front of the screen, the first quantity is causally determined in part by the second quantity. The type level version says a quantity of this type and a quantity of this type applied to objects of these types with this relationship between them has a QProp between it. So in other words, this caches out to, for all x for all y, if x and y are gaseous objects and x is the same thing as y, then the pressure of x is qualitatively proportional to the temperature of y. Okay, so that's the translation to instance level. But you do the reasoning at the type level as much as possible. Now, if you're dealing with generic statements, like you're reading a simplified version of the Free Civ manual, this is a true blessing. So here's a little bit of a manual, and here's the translation after the whole abductive reasoning process has happened on the first sentence. It's detected, I've written this in frame-like syntax just for easy visual processing. Normally there's a lot more parentheses and they're all independent statements. So we've got a type level process that's a generic production process, and that kind of event is actually tied to the language in the site KB. We didn't introduce that. There's some event it refers to a production from the sentence. That's a discourse variable. It's done by something that's a free civ city. The output's created as something that's a type of amount of food. And there's a positive influence of the amount of food of the rate of production. Now you take the second sentence, and remember this, because you'll see it again here. As the population of the city increases, the food production of the city increases. And so this is actually a classic qualitative proportionality introduction. And so it's saying it's a positive qualitative proportionality, and the constrained quantity is the rate of food production, and the thing that's governing it is the city population. And finally, a citizen consumes food from the city. You're introducing another process. Notice it's a destruction event, another kind of thing from the ontology, and now you're filling out its dynamic consequences. These qualitative models are very powerful. So one of the things about strategies in games like this is they involve trade-offs. Analysis of the qualitative model can identify trade-offs and let you reason about those. Now, even a little bit of advice improves performance.
Time represented in the previous slide?
Because these are all things that are happening continuously while the process is active. So in other words, it's a mechanism by which behavior is generated as opposed to the description of the behavior itself. We have other ways of describing the behavior itself. Okay, so turns out these type level representations are very useful for advice. So irrigating a place increases food production. Absolutely true in the game. Adding university in a city increases its science output. Now you take a half dozen pieces of advice like that, and you basically say, okay, how well do I do at producing science? This is averaged over 10 different games, and by 97 turns, it's still, the experimental condition is still doing better on population. Not hugely better, because that's not what it's optimizing for. It's optimizing for science output. Here, you're getting to the point where you can build libraries and other units, right? Before that, you couldn't build them, and so these two look pretty much the same on science output. But now the advice kicks in, and you start getting more science produced for the cities. Okay, so that's one modality, and it's also a little bit of the game learning. Now, what about the other modality? Sketching is a very natural way for people to communicate knowledge. This is a picture of a geologic formation, and if you're an instructor in geoscience, what you want to see when students mark it up is something like this. That's the fault, the main fault. These are the directions of movement. These are called marker beds, and these indicate the displacement of the marker beds. Okay? And we've actually built something with our sketch understanding system that handles things like this. It's domain independent, which is very important for us because we want this to scale. In an experiment at University of Wisconsin-Madison, a geoscience grad student made 15 worksheets and showed significant gains pre-post using those worksheets in their intro geoscience class. We've had similar results with a unit on the heart for 5th grade biology. And we're about to go back into the classrooms in an engineering design course for learning engineering graphics. And we have independent evidence from laboratory studies that you can actually do assessment by looking at what order people draw things in a sketch and what they include or don't include when they're annotating diagrams. This is a massive effort involving a lot of people. He's a well-known structural geoscientist. Bridget is the grad student who actually cranked out the worksheets. She's really good at this. Maria and Jeff are two of the CogSketch developers. And so that's the whole talk there, but I'm not going to go there. I'm going to instead pivot to other roles of sketching. So sketching is also a tool for thinking.
Completely. Can you say a few more words about the ordering effects?
Okay, so if I have, for instance, a photosynthesis diagram, then a student who doesn't know photosynthesis will start with the most visually salient parts. A student who understands photosynthesis will start from the input and go through the causal chain to the output. Very simple to catch. And if you've got digital ink, you can know what order people drew things in. And this has happened in a couple of domains now. Basically, if a student understands a domain well, for instance, geoscience, there's certain things they'll pick up versus certain surface features that literally are irrelevant. So it's pretty easy to, it's not rocket science to tell the difference. It's not a subtle signal. Okay, so this is a sketch by a painter, Shona Trescott. She was on an Arctic expedition. You'll see some little stick figures here. You'll see some notes about the background, no distinct horizon, disappearing figures. And so in the Arctic, you can't really paint, okay? And even if you're in a more genial climate, artists often do this. This is the painting that resulted. So she's perfectly capable of doing all sorts of very fine, subtle visual work, but to just think it out, she first did a sketch. And this is pretty common. Sketching is an aid to thinking. And so what you'd really like is systems that can sketch with us and sketch for themselves in human-like ways. So here's the long-term vision. You want a software that understands sketches as people do. Now, what does that mean? So here's a ramp and a block under gravity, and you can infer the block will slide to the right and down. Perfectly sensible. Now, that requires fluent natural interaction and human-like visual and spatial reasoning and conceptual reasoning about the contents of the sketch, and you want it to be domain general. If you look at the sketch recognition literature right now, every subproblem in every domain is a separate system. You have to train the recognizers anew, you have to build new software. That doesn't scale. That's one of the reasons why we've done some engineering workarounds for segmentation and conceptual labeling. We actually don't do recognition on the whole, okay? Because it turns out you don't need to. When people are talking to each other during sketching, that's how a lot of the labeling happens. It doesn't require recognition. Recognition is at best a catalyst. You look at the speech recognition research, it's focused solely on that topic. And we're focused on the rest. So even if recognition were perfect, and there's reasons to suspect that it can never be perfect at the level you need it to be, especially for education purposes, you still have to do what we're doing. Let me show you what that involves. Now, the thing I'm about to show you is actually something that you can do yourself if you download CogSketch and fire up the design coach and ask it a question about the behavior. And what I'm going to show you is basically a rational reconstruction of the reasoning in the truth maintenance system that the system's actually doing. So here's our ramp. So we have the ramp and the block, and CogSketch recognizes visually that they're touching directly, which causes it to extract an edge representing that surface contact. It computes the surface normal of that because that's very relevant in terms of how forces transmit. It's in quadrant 3 here. That's a qualitative way of describing angle. And now you think about gravity, and we're now using some of John Wetzel's qualitative mechanics work. You have a force applied to the object in the downward direction, and that is the only force on it. We're assuming the friction doesn't matter here. And so now you have a translational constraint from this edge saying it can't move in the downward direction. And that, plus a little bit of other reasoning, says, well, the translational motion will be in quadrant 4, i.e. to the right and down. And that's how it infers that stuff. Now, it turns out there's two parallel literatures, one in artificial intelligence about qualitative reasoning, and one in cognitive psychology that they call categorical coordinate, and they're the same thing. And they're interestingly complementary literatures. So the other thing is that structure mapping processes are used in visual reasoning. So let me show you some work from Andrew Lovett's thesis. So geometric analogies. A is to B is C is to one of those. If you download CogSketch, you'll see all of Evan's problems in a sketch that you can play with and experiment with. Andrew's model has the lovely feature that, of course, it gets them all right. This is a very easy task, it turns out, and it makes reaction time predictions that are borne out in human behavioral experiments. In fact, there's a later paper where by adding working memory constraints and two strategies, which is the model that actually you can play with in CogSketch, the correlation coefficient is 0.9 something. It's insanely good. I mean, it really is a simple task. A much harder task is Raven's progressive matrices, which is commonly used as a test of fluid intelligence in humans. Andrew's model is better than most adult Americans, and again, it makes reaction time predictions, and what's hard for people is hard for the model and vice versa. And finally, there's an oddity task that DeHaan and Spelke used to look at cross-cultural differences in geometric processing between Americans and Munduruku. Andrew's model, again, same representations for all these things, all automatically computed from PowerPoint stimuli, copy and pasted into CogSketch. Andrew's model, again, solves most of the problems. What's hard for it is hard for people and vice versa. And you can do ablation studies on the models, obviously not the people, and get some insights as far as what's happening across these different cultures. Okay? Now, at the risk of putting everybody to sleep, I'm going to switch briefly to a video. And this is showing you a companion learning tic-tac-toe.
A demonstration of flexible multimodal instruction in a cognitive companions architecture. And we're going to teach our computer to play tic-tac-toe through a combination of natural language and sketch interaction. So we introducing the topic. And I say I'm going to teach you to play tic-tac-toe, and this provides some expectations about how to interpret future statements.
You'll see the predicate
So
calculus coming down here,
create
by
a
the
new
way.
sketch, and I start by classifying the game. And I say tic-tac-toe is a marking game, as opposed to a piece-moving game or a construction game. And this tells it to expect some kinds of marks, as well as a board. Now we're going to draw the tic-tac-toe board, and it doesn't know what this is, and it's not recognizing the ink or anything. But the board is going to be the background, and we're going to explain what this is in natural language. So I type tic-tac-toe is played on a 3x3 grid of squares. That contains a lot of information. It tells us that there's a spatial configuration, its Cartesian coordinates, and the maximum extent of any dimension is 3. And on that basis, it's able to label the glyph we just made as the board. Now we go on to classify the game some more and tell it that tic-tac-toe is a two-player game, which means that it can expect us to introduce some player roles. So X is a player. It understands that to mean that X is a game player, not an athlete or a musician. And we can now draw an X, and it doesn't recognize the X, but rather it understands in context that this must be the X. And so you can see that it labels it with its own little X below it. Now I can proceed to make an O, and I can do this before I've introduced the player. It doesn't recognize it, and I entered O as a player, and we can see that it understands and labels the O. The next thing we do is describe the actions in this game, and I tell it that X and O take turns marking empty squares. That contains a lot of information about turn-taking and the kinds of marks it makes and the precondition for making marks on empty squares. The next thing we enter is a description of the goal, and we're only describing one goal here. We're saying that the first player to mark 3 squares in a row wins. It only understands row to mean horizontal row, not a column or diagonal. But through demonstration, we will teach it the other win conditions, such as vertical columns or diagonals. And then X goes first is highly ambiguous and context sensitive, but it tells it who starts the game. And at this point, there's enough information in this representation to play a legal game, so I tell it to start a game. And what it does is it takes those marks I've made, and puts them in a catalog, a separate layer, creates a new layer for the game state, and made its move. It made an X in the middle left square, and I respond with an O in the center square. It's playing a blind, random game. It doesn't understand strategy yet. So I'm going to be a little cruel here, and I'm going to demonstrate winning by a diagonal. So I mark 3 in a row on the diagonal. And in order to help teach it a new rule, I select the winning configuration.
Our way of doing didactic reference in sketches.
It doesn't know that it's lost yet, so I tell it I win. It takes the winning configuration and creates a new rule for winning on the diagonal. We can inspect this rule if we look in the command transcript window. In this case, the rule is specific to the particular diagonal, so it will require another trial to learn the opposite diagonal. But if we demonstrate winning on a vertical column, it will generalize this to all columns, analogously to the rule it already has for rows. So we only need a total of 3 trials to learn the complete rules of tic-tac-toe through a combination of instruction and demonstration. This concludes our demonstration of flexible multimodal.
So if that middle vertical column was not a win in this special variant of no vertical win tic-tac-toe, what would happen at this point? You generalize, you say, oh, I've generalized it inappropriately, and back off and create a special subcase.
Except this version won't. Actually, if it learns a bad rule, it's hosed.
It's really hosed. It can't go,
This version, no.
Refinement.
Right. Yeah, no, we're focusing, I mean, for that project, our focus was entirely on what you have to do in terms of multimodal interaction to bootstrap these things, okay? Okay, so what was going on under the hood there? You've got your language coming in, translated to a general logical form, predicate calculus interpretation. It's interpreted in terms of communication events and instructional events, so it understands how to interpret them. And in some cases, we have to fall back on general heuristics to do interpretation. In this case, no, because there's enough knowledge about the context. I'm being taught a game, okay? And that's an incredible driver. The digital ink gets turned into symbolic representations also, and interface gestures like they just added a glyph and things like that also get turned into the same communication stream, and that's what leads to building game rules. So the interpretation process, as described earlier, this turns out to be a lot of fun because the psych knowledge base has a boatload of stuff in it. In an earlier system, we talked about the Jordan River enters the Dead Sea, and I thought there was an entering the container event where the container was the musical group The Grateful Dead. Okay, so you get all sorts of amazing things if you have something that knows stuff about the world. And it's sitting there basically interpreting these things to where it gets down to a point saying, well, X plays the role of something in a game. And there's a whole set of instructional events. If you look at the intelligent tutoring literature, this is a spin on some of the kinds of instructional events you see there, but game specific, like for instance, win conditions is not something general, but defining configurations, that is pretty general. Entity introduction and action generalization are pretty general. The game classification is from earlier work on GDL, is basically nothing that we really added ourselves. And communication events, there's both the stuff from language and the stuff from interpreting what's happening in the sketch world. Now where we're going next with this, we've done hexapon, that's kind of trivial. The only difference is it's a piece moving game. Tom actually can now describe all the regular moves of chess to the system by language and sketching, okay? Can't do castling, capturing en passant, and pawn promotion. And all those things are things that you really want to do by language. You really don't want to do this by demonstration, right? How do you say you can't castle if the thing hasn't moved? That doesn't work so well. And we'd like to then expand to discussing strategy as well as rules for play. Now, spatial concepts. One place we've done this is FreeCiv, where we looked at geospatial concepts. we can map a free-sieve map into CogSketch and sketch on top of the map. And so here, Matt has basically said, drawn a circle and said, this is a straight. And what it causes it to do is take the encoding of that region and shove it into a generalization context for the word straight. And it's using that to build up a model of the concept. And then you can then draw circles elsewhere and ask it to basically classify those things. And it's basically saying, if I do analogical retrieval over my encoding of this across the whole set of generalization contexts for the concepts, then which is the strongest match from? And that's its way of doing classification. And this is okay. I mean, you know, 60 examples, 10 per concept, tenfold cross-validation, about 76% accuracy. I'm not excited by that, but when you look at similar tasks in this world, it's not out of band. I think we should be able to do much better, but one thing I worry about is overfitting. So it's always dangerous to just use your own data. So there's this lovely corpus by some folks at Berlin and Brown. And what they did was they took 250 concepts like snowman, ice cream cone, giraffe, grapes, bunny rabbits, airplanes, etc., and got people on Mechanical Turk to make 80 sketches per concept. So that's 20,000 sketches. Now, they claim in their paper that this exhausts everyday objects. I don't believe it. And it includes things like hand grenades and flying saucers, neither of which are everyday objects for me, and especially I hope not together ever become everyday objects for me, okay? But it's still a great corpus. It's very tough. So here's the experiment. What they did was they used pixel-level image encoding properties and machine learning classifiers, and we're using CogSketch encodings, because it's all ink, we just suck it in, plus analogical learning. Now we started with 10 concepts. Why 10? Both run time, because we have not engineered this in the way we need to do to scale up for large batch experiments, but also another problem, as you're going to see in loving detail in a minute, okay? Because some of these things we just can't do yet, and we know why, and we have partial solutions. So encode with CogSketch, 8-fold cross-validation, and those numbers of concepts. Typically when we do analogical generalization, within 12 examples, we've got as good as we're going to get. The only example before this that was different was counterterrorism. There we needed about 30 to figure out who the perpetrators were in some events reliably. So this was how they broke it up, so we encoded it their way. So here's the results for 3 versions of our system. These are 2 extremes in SAGE. This is the knob where you say, I want everything to assimilate. I set my assimilation threshold so low, it always merges everything into one model. Okay. This is turn it the other way. It has to be a perfect match before you'll assimilate it. And so it's a way of doing both prototypes and exemplars in the same model. Align is like these 2. It's using SAGE, but it also has near misses, automatically derived near misses. If you get something retrieved from a neighboring concept that's mutually exclusive, that's obviously a near miss. And so it actually constructs small hypotheses about what those differences are that in some cases significantly help in terms of telling them apart. Now here, the differences turn out to be not so much. And if you look at the pixel level stuff, it's also about 56%, but overall 250 categories. Okay, so for the categories we can do at the moment, hey, we do about the same as what they do, but there's 2 things that disturb me about this. The first thing that disturbs me is, you know, why so low and why so slow? The second thing that disturbs me is humans are up there by a Turk experiment that they did on their data set. That's a lot of headroom, okay? That really bothers me, because usually we get human-like performance in a small number of examples. So what's going on? Well, if you look at it close, here's at least one thing that's going on. There could be others. So if you take a turtle, this is from their corpus, here's a visualization of the CogSketch analysis of it. So it breaks things up into edges. You can see the junctions between the edges. It also constructs edge cycles, connected sets of edges. And these things often are cool because they segment stuff into objects. And these edge-connected objects are sort of higher-level descriptions that group those things, okay? Now, bad move. Instead of just picking one level, the one that's most informative, we threw them all in. Okay, so that's a lot of facts. So that's 464 facts for this turtle. Now, in other experiments, it looks like for analogical matching, if you can't do between 10 and 100 relations per description, you're not in the game. You're not going to understand stories. You're not going to do moral decision making. You're not going to do visual processing. You're not going to solve textbook problems. But this is a lot. And now, when you start doing more textures, it gets worse. Okay, so a lot of texture in this turtle, right? A lot of regions in this turtle. And so what do you think's happening? So here's a principle we're trying to extract out of this. That part of the goal of encoding processes should be to construct concise informative representations. And we've always worried about informativeness, but we've never really worried about conciseness. And with perceptual processing, that's a mistake. So we think of this as going to be an internal metric on the cognitive architecture. You start thinking in terms of upper bounds on assertions and trying to extract away when you have that. There is some evidence people do this, but it's very weak evidence. I would not take it to the bank.
Representations, or just a way of separating essentially figure and ground, or so that it may be a layered representation?
Oh yeah, no, we're assuming layered.
Okay.
So Cogsketch actually has four different layers of representation. So it can do groups, shapes, groups, objects, and edges. And there's a fourth thing in terms of surfaces. And it'll actually dynamically move from representation to representation. Couldn't do ravens without it, for instance, or the oddity task. But we have to add more. And this is a clear, if you're thinking of this in vision terms, this is a texture problem. And so we're looking from the vision literature at a planar icing model to handle these regular repeated structures. You basically take a whole bunch of them that are similar in some way and turn those into a description that's one big chunk of stuff and it's got a whole bunch of things that are about this size and about this eccentric and all that. So you've basically re-represented it. Now that works for some of the turtles. Works nicely for this one. And this one, oh my God, that was a nasty little turtle before, right? Because look at all these different textures in there. Works for this one. This is all one unit now, and it's got some extra properties of it, talking about the visual properties of the things inside.
That's what you're doing here to abstract away from
So the idea of these icing models is you say, I'm going to put basically little control points at these various spots and say, can I get rid of these? Are these things sufficiently alike that I can merge them together into one unit? And then you do some energy minimization over that.
I don't understand that.
Well, we didn't invent the technique. We just got it off the shelf.
Okay.
But
So
think
it's for
of
texture
it like
detection, right?
what?
Icing models are for texture
Yeah,
detection, right?
and we're treating this like
So it would be
texture.
hard to do for hair, for example, where there are not,
Yeah,
I don't know, like strands of hair might be repeated.
yeah, and people put in what the sketch recognition community calls adornment or decoration, right? And yet people do that, so you really have to learn how to handle that. Now that works sometimes, does not work all the time. So here, it didn't actually figure out that you should group these things that way. Here, it turned the entire turtle into one big blob. Okay, so we're still trying to figure out what's going on here. Now I'll close with one more example, and this is learning to do inference on structures. This is not a problem we picked out. This is a machine learning community problem, and so the idea was, well, you've got the semantic web, which is growing by leaps and bounds. You've got the whole knowledge graph thing in Google, and I'm sure Microsoft has an equivalent thing. I'm sorry?
Sartori.
Okay.
Yeah, it's your slide next time.
So can you do traditional logical inference? Sort of, but the data is incomplete and noisy. Statistics, well, they're structures, not feature vectors. So if you're a dedicated machine learning person, you'll say, we can fix that. We can vectorize those suckers, okay? So you make a distributional vector space, you take the relations, you mush those into vectors, and you crank around, you make a tensor network, and you do stuff, okay? Now, I think it's sort of sad. I think feature vectors are not as expressive inherently as relational representations. And if you had the structure to begin with, it's really a mistake to not exploit it. So you get good accuracy, but it requires a lot of examples and it has to train over all the relations at the same time, and it lacks interpretability. You get this number, that this is the best one, you can't say why. Let me show you a better way. So you build cases for analogy by pathfinding. And the insight here, which is not unique to us, is if you have a relation between two entities, they're likely to be indirectly related to other in a bunch of other ways. And as usual with these sorts of algorithms, you put in limits on branching and search for tractability. So parent of one person another, you also generate negative examples by corrupting that triple into something else. And that's the same technique that these folks use. Now what we do is we basically search through the database and grab a bunch of relations, tying those two things together, and those become a case. And we only grab 10 positive cases and permute those to get 10 negative cases. 10, remember that number. It'll come up again. Then for template learning, we do analogical generalization. And so we basically take two cases and we match them to find out what corresponds. And then we basically use Sage to construct templates. If after this match, if these are mushed together, then these only appear in one, so they're going to have probability 0.5. These appear in both, they're going to have probability 1.0. And if you keep going, you can see the things that aren't in common are going to get smaller and smaller probabilities, and the things that are in common stay high. Okay? Now, you can do better. The usual way we do these things is just say, hey, we use SME, and we let that be that. Now, what Chen figured out was, okay, there's cases where some properties are really for a task more important than others. And you'd like to learn what those are, and you'd like to bias the match. So think about the numbers computed by a structure mapping computation, and now convolve that with task-specific importance weights. And so he computes those by extending logistic regression to work on structured data. So think about an analogy between vectors and a structured case. Dot product becomes structure mapping. Vector addition becomes structure addition that Sage is already doing with the alignment step. And then you train with gradient descent, etc. So if I've got the traditional way of doing it with input vectors, each vector position tells you what goes with what, so that's trivial, and then you get your dot product. With structure mapping, these are expressions now, and I have to compute what things go with each other, and then I get my stuff that then I can train by gradient descent. How well does it do? Well, so there's two data sets that people have used for this. They have a WordNet data set and a free-based data set, looking at 11 and 13 relations respectively, large test set, whole bunch of training data, and the other models use typically 10,000 training examples and train on all relations at once. We use 10, and we can train for each relation independently. You add a new relation, we don't have to retrain on the others. And how does it come out? That's the scoreboard. That's our system. And you notice the top systems in both cases are not the same. And so we're right up there. We're not the best on either corpus, but we're right up there with 3 orders of magnitude less training data. I think it's pretty cool. I'm excited about this. And you know, we've done this plenty of times before on data sets that we found or generated from our reasoning systems. But to be able to do it on data sets that the machine learning community has done and get the same performance, we're very happy about that.
Do you gain anything with more training examples?
Not at the moment. And we're trying to figure out why that is.
And are the examples randomly chosen? Or
Yeah, they're randomly chosen.
Space in an interesting way based on like density?
Randomly chosen. Now, the other thing it gives you is explanations. So you can say, basically by sort of evidential explanations, what's in the matching, and this is deliberately chosen to not be interpretable easily. So if you had a natural language generation system to test your knowledge, you'd have a hypothesis like saying, well, this person is Tongan, and you ask the human yes or no, and they're going to say, right? Unless they have a lot of world knowledge, in which case, why are you learning this knowledge? But you can say, well, his parents is Tongan, and a person from the same country as him, his ethnicity is also Tongan, and then you can look at that explanation and now have more context. You have some knowledge about the reason why the system believes that. And we think that's also very valuable. And so by sticking with structure, you learn faster and you get explanations, which are not inconsiderable advantages. So just to wrap up, for some purposes, bespoke data is better than big data. If I'm trying to train software assistants, and I'm looking at you, Cortana, you want to say something to it once, like, never show me Fox News in my notification stream ever again. I can't say that. Or I can say that, it won't listen. You want human-like learning of tasks because you want assistants to be at least as good as we are at learning about the tasks that we're training them for. And rich knowledge supports learning from bespoke data. So we didn't use analogy in learning tic-tac-toe, we actually just talked it through. And because the system knew about games more broadly, and knew about sketching and knew how to connect those things and knew about instruction, it was able to interpret that information in a way that mattered. And if you're doing learning, structure mapping can support learning with a small number of examples. And better representations, like sticking with structure when you have it, can drop your data needs by 3 orders of magnitude in the case we just saw. And we think that's true more broadly. A little joke here, just like orange is the new black, structure mapping is the new dot product. Okay. So I end by thanking all the people who really made all this happen. Thank you. Questions? Yeah.
So you mentioned early on in your talk, you mentioned the word understanding.
Yes.
Do you have a definition for that? What does understanding mean?
That the system constructs representations that enable it to do the kinds of things that we would expect people to do given that same material in the same context.
So the only way to measure if a system understands is by having humans in the loop.
Or by measuring its performance in some other way. I mean, so here's an example from another study we've done. So you take little kids and you give them a forced choice task where you have things that are the same in one dimension versus another. And it turns out you can pick the task so that 4-year-olds can't do it, they're at chance. 8-year-olds can do it, okay? And then by cleverly reordering the stimuli, you can get 4-year-olds to learn it, okay, without feedback, okay? And this is something Deidre Gettner and her student Laura Kotowski did quite a while ago. Now here's the cool thing. If you're going to simulate that, you need to do 2 things. You need to figure out how to do the forced choice task. In this case, it's, are these things similar enough? And which of these is more similar? And you need a signal that says, I'm not doing it right yet. And so how do you do that? Well, in a forced choice task, if my encoding of the situations is not sufficient to make it clear which one to pick, I know internally, without someone telling me, that this is not a good encoding. And so the system actually casts about a bit to figure out what a better encoding is, and then snap, it gets it, okay? And so internal signals like that we think are critically important. And so we're kind of on the lookout for those now, right? Which is why on the encoding thing and conciseness, we're now thinking that should be a big signal. If you're getting too much stuff, you're clearly encoding it wrong. And you have to think about this thing differently. And whether you get advice from people on how to do it or you have to search your own space of alternatives, open question. But I think those internal signals are also crucial. One thing that happened in Learning Reader is you could have the good news, there's good news and bad news. If you want to detect surprise, then you could give it some new example. And if it's been building up an analogical model of something, and it's got a bunch of examples in it, and nothing's retrieved, that's a surprise, right? Because if you've really seen all the space, then you should get something. Now, it turns out the bad news is there's 2 reasons for that to have happened. You really are seeing a different part of the space, or you have an error in your natural language understanding system. And then as you get more things with that same error, telling those 2 situations apart is really hard. Okay, so that's the downside of it. AI's hard.
Maybe Ken, it would be fun for you to share some intuitions that you shared with me earlier about the approach that you've been taking over your career with cognitive architectures and results coming out of some of the larger scale big data approaches. I know that was themed for your talk, but like, you know, the Atari game learning by DeepMind and other groups that have been doing that kind of thing. We're thinking of something along these lines as a general community challenge problem in larger spaces, like more complicated games. People that look at general connectionist, use the old name for it, style models that promise to learn from data and potentially supercharging those someday with these kinds of abstractions versus starting with the abstractions, using a little bit of learning on top. Just your thoughts on methodology and approach. Some people say that those methods will sooner or later bury these more human authored kinds of approaches, even when humans just try to big boxes, put arrows between them.
Well, okay, so if you think about what we're doing, we're making the bet that you can safely package off a lot of the perceptual processing and hand jam that. So, for instance, our CogSketch, for better or worse, is our model of 2D geometric processing in vision. It doesn't do everything in vision by any means. Think about texture, color, shape from shading, just a raft of problems it doesn't try to address, but it's a sweet spot for interacting with people. So, you know, gerbils learn in slow ways, as do people. Right? If you think about how long rehabilitation takes after an accident, physical therapy takes forever, right? Because our motor learning systems aren't that fast, and you probably wouldn't want them to be that fast. They'd over-adapt in bad ways. But the stuff that humans can do that's pretty darn amazing is couple the stuff that lets you interact with the world in reasonable ways with all this amazingly complex conceptual knowledge. And so I think if I were to make a bet, and I have made this bet, you know, we're going to have human-level AIs helping us figure out how brains work rather than understanding about how brains work be central in making human-level AIs. There's an analogy that Ken Ford and Pat Hayes did with AI and artificial flight. And they pointed out the first flying machines did not flap their wings and did not have feathers. There were plenty of attempts to make those at that time. But the ones that didn't and succeeded basically said, we're going to understand the principles of flight, so the principles of intelligence. Now, to understand those principles, I still take a lot of guidance from humans, because humans are the best example we've got, but I'm also willing to look at other animals, okay? And so eventually, in fact, now materials have gotten better and different. The people are trying to build flying machines that are like birds. But that's over 100 years later. And I think that's what will happen with AI too. You know, eventually we are going to have one story that goes all the way down and says, you know, these dopamine receptors hook in all the way up to, you know, your knowledge about intention, you know, Meltzoff's like me hypothesis, where think of it as an analogy between yourself and other people, right? I can state that hypothesis without talking about dopamine. And I can have a completely good scientific model of conceptual reasoning without knowing about neurons. And so that's why I'm betting the way I do. And I'm glad other people are making other bets, because I could be wrong, and ultimately the whole story's got to all hook together. And so you really have to have all these things going on. But so you guys are going to do some game learning?
We can talk offline about it, but
okay.
I actually want to get your opinions.
Oh yeah, I think games are great. So we did the sketch games as a DARPA seedling. No more money for that, alas. But I do think it's a kind of platform where you can imagine really open-ended conversations.
We can understand later because we got to go public with this talk. I want to just talk about it offline.
Yeah, okay.
Everybody out there.
So, but like, if you think about the way people are playing Go or chess, it's not very human-like, right? Think back to the old Chase and Simon results. So one of the reasons why we're doing this is we'd love to make a companions executable that has a sketch game capability built in, as well as a whole bunch of conceptual reasoning built in, so that people could then experiment. And I'll bet you that you could make a really cool, like human-like chess player that could really explain what it's doing in terms like those you would see in a chess book, for example. Okay. And even if it wasn't the best chess player, hey, it would still be kind of cool.
Any other questions? Okay, thanks very much.
Thank you.